learning so long time from both of them. They are expertise in the oil and gas industries. Even we learn from them so much. So this is the time that we can share some of our knowledge with the community under their supervision. But I know that the last lecture was a little bit challenging for some of the students. So I will try to make myself a little bit slower, and I will stop while the presentation to get some questions. And I'd like to ask the guys there to be patient while the presentation, because we are going to cover some theoretical equations in addition to some practices. But how the day will go with us? We'll start with introducing some. We are going to introduce the simulation as concept and principles, and we'll introduce some theories. Because I know that not most of the students are quite familiar with with the simulation. That's why I will start introducing some theories. This will be a little bit challenging for some people, so please be patient with us. So then I will take you through some applications. I will show one case study. Then I will hand over to my colleague Mahmoud, who will take you through the software. He will show you via the software. He will use T-Navigator today, show you how to implement the simulation to develop a field, and he will show some application on streamline simulation and the tracer. Okay, so again, I'm going to start. So if you have any question, just and I will answer immediately after a couple of slides. Okay. Thanks, Karim, for helping me. So please share with me whatever question you think is important relative to the slides. Okay. I'm going to start quickly saying, giving introduction to reservoir models. I will use Arabic a little bit while the presentation. I will not use the Arabic for the whole presentation, but I know because most of the students here will find the topic a little bit challenging, but I will use the Arabic for a while. And if any one of you thinks that if I present a slide in Arabic will be much easier for you, please ask me to repeat it into Arabic. Don't worry and don't feel shame about that. Okay. So reservoir models, we have, like I show you here, we have two types of modeling. We have physical models and mathematical models. And physical models, like building a real case using electricity, for example, electric circuit to represent something. Okay, this is something we'll not discuss it today, but what we are going to discuss is the mathematical models. But the simulation is coming as part from, to take you quickly, this is the physical models, building scales and elemental models. It can be like electrical circuits and etc. So this is not part from our presentation today, so we are going to skip it. Then we have the mathematical models, and the mathematical models include two types of models: analytical models and numerical models. Water flooding is very famous with analytical models, and I think I explained some theories and some models in the last session. Like I said, like leverage, like styles, like diets, and etc. You can calculate the recovery factor using different models, using the displacement efficiency, vertical displacement efficiency, area sweeping efficiency, and displacement efficiency. But today, we are not going to discuss further those analytical models. We might have another session to put some lights on those analytical session and discuss them in more detail. Today, we are going to use another type of models, which we call it numerical models. And numerical models, it comes out to be the simulation. Okay. Again, like I say, I discussed this for the water flooding. I discussed a few models, but for analytical models in general, we have the material balance. For example, I have the owner to be with you in the project, graduation project, and all of you quite familiar with the material balance. You did a good job with decline curve and aquifer description. Those three models, we call it analytical models. Okay, and they are quite simple and they have so many assumptions, and we had enough time to discuss them during the graduation. What's good about them, they give exact solutions. So, but this is not the area which we are to discuss in detail today. What we are going to discuss in detail today is the numerical models. And the numerical model is simulators and use well-bore hydraulics in the calculation. It's very complex. Use both reservoir and fluid flow descriptions. It's approximation solution. It's not exact solution. Like you know that material balance, for example, you can drive the material balance, then use it in the straightforward in the solution. That's why it gives you exact solution. So it's like 1 + 1 = 2, which means this is exact solution. 1 + 1 cannot be 3, for example. This is exact solution. But for numerical solution, there is no exact solution. This is approximation to many equations together that come out with a solution that even multiple solutions that can represent your scenario. Okay. I said, please be patient with me because this topic is really challenging, and I have to take you through the theory before I'm going to take you through the application, because I know most of you are not quite familiar with the theory. Numerical simulation is used for resource management. When I say resource management, I mean oil and gas resources. Some people using the word reserves, but whenever it's not mature, we're still calling it resource. So this tool is used to manage the oil and gas reserve or resource, and we can make forecast out of it. So usually, like I said last time, if you have a field with oil and gas, you need to understand how many wells you are going to drill, where you are going to drill those wells, how much recovery factor you get by doing that. So you have different scenarios, and at the end of the day, we need to make the maximum profit, maximum money out of this field. It's not only maximum production, we need to get out of the field the maximum money. Okay, we need to get the maximum profit. Those models, we build it by integrating different pieces of information, going through from geology to production to fluids and rock properties. We bring all those together, then we calibrate it to the production, to the real data, and you use it for forecasting the performance of our field. Okay. It's something very quick here. I'm showing you what you get out of the simulation. Usually you get the oil forecast, production forecast for different scenarios. This is something we'll also spend some time with it later. Okay, you have to just to build this model, you need geometry, you need to understand geology and bring the geometry, you need to production strategy, you need rock properties, fluid properties, and drive mechanism, which is represented here via. Okay. Then you can predict the different parameters like the water cut, the GOR, and like I said before, the oil production. Then what's numerical modeling? So I will spend some time describing what's numerical modeling. But reservoir models are simplified mathematical abstraction for reality. And if I just bring the numerical simulation to you, I just would like to remind you, with any architect, when you try to build your home or your house, you go for an engineer. He's different discipline. He might be civil engineer or architecture engineer. Anyway, he built for you a picture or 3D for your building, or for the interior part of your building, from outside or inside. We call this as a model for the building. This is not a real. This is a model for your house. In Arabic, I would say it again. لما انت بتروح تبني بيت، فانت في الاول خالص بتروح تديه للمهندس المدني او مهندس المعماري، تقول له انا عاوز تعمل لي تصور للبيت ده قبل ما ابنيه. فالبيت ده بيبقى فيه ليه حوائط وليه الاعمده بتاعته. he shows the columns, he shows the bars, everything in the building he put it for you in 3D. That's why you can predict how it looks like from the beginning. What if you do this, and if you move furniture from here to there, how it looks like, how much will be the total cost at the end. That's why we are, as petroleum engineers, we have more challenging realities that we need to model. This reality is our reservoir. This reservoir is 3 kilometers, usually is 3 kilometers under the ground. So it's really far away, and it's not possible that you see it. You have to bring the data, collect all the data together, and build a 3D visualization for your reservoir. Okay. So I will take, before I'm going through the simulation, I'd like to tell you about how we derived the simulation equation, and it's quite familiar, famous equation. We call it diffusivity equation. So I will not spend so long time with the diffusivity equation, but I will tell you how we drove the diffusivity equation. It's mainly coming from 3 equations. The first one of them, we call it the mass balance. The second one we call Darcy law, and all of us are quite familiar with mass balance, Darcy law, and to bring at the end the diffusivity equation. Okay, those are some topics I will spend some time with them. Finite difference, truncation error, and etc. And what's the difference between implicit and explicit solution for the simulation. Okay, so do some topics. I will show it after a few minutes. So usually, before we go into the simulation, usually simulation remind us with the cube. And we need to understand how can we model this cube. If the fluid is going inside the cube and getting out of the cube, simply in Arabic again, if لو انت عندك قطعة مكعب صغيرة وفي فلويد بيدخل المكعب وفي فلويد بيخرج من المكعب، في النهاية البريشر داخل المكعب is going up or going down. It depends. The pressure inside this cube is going up or going down, exactly like balloon. If you what is going inside is more than is getting outside, the pressure is going up. If what's going outside is less, is higher than what's getting inside, the pressure is going down. So exactly like balloon. So this is what we call it mass balance. Okay, and the mass balance is I'm not going to spend so long time with it. It's quite easy. Usually, if you have a volume, the volume like rho is the density multiplied by the area multiplied by the length divided by the time. This will be the mass n. Mass n is like rho, which is the density multiplied by the volume and divided by time. This will show you the accumulation into the cube. And from in and out. And what's inside the cube is the volume of the cube. What's the volume of the cube? Reservoir cube is the density multiplied by the volume multiplied by the porosity. Okay, And if we put them, so we can say that what's getting inside minus what's getting outside equivalent to the increase in the volume inside the cube over time. This is the equation. It looks a little bit challenging if you don't derive it from the beginning, but it's quite easy. Density multiplied by velocity divided by the distance will be equivalent to the density multiplied by the velocity divided by the time. Okay, this is a little bit challenging. So before I move, if anyone has any question about this slide, I can take it right now. Karim?
No questions for now.
Okay. تاني بالراحة, I know that we have some foreigners on the call, so that's why I try to keep myself in English. تاني, انت عندك فوليوم داخل وفي فوليوم خارج, والانكريس في الفوليوم جوه الكيوب ده بيمثل لي التغير في الفوليوم داخل الكيوب. احنا كلنا عارفين ودرسنا في الهيدروليكس ان الرو في الفي رو في فوليوم بيساوي ماس, والماس الماس عشان يبقى ماس ان وماس اوت, بقول الماس اللي داخله ناقص الماس اللي خارجه بيديني تغير في الماس داخل الكيوب. الماس جوه الكيوب عباره عن ايه؟ عباره عن برضه رو في فوليوم, بس الفوليوم داخل الكيوب فيه بروستي, فانا بضرب الرو في الفوليوم في البروستي واقسمها على التايم, فالاثنين بيساووا بعض. خلاص, ده المعادله دي very simple equation. If I'm moving forward, this is equation, but we have another source coming to the equation is the rate. Whenever you drill a well, we add the production of the well, or if we are injecting the injection of the well to the equation. So this is a small cube, either has oil production, fluid production due to production well, or fluid injection due to injection well. This injection well can be gas or water. Okay. Then it's quite simple, Darcy equation. I'm quite sure everyone familiar with Darcy equation, and Darcy equation gives us the relationship between velocity and the pressure. And we know that the velocity increase whenever we increase the pressure difference. And what's the relationship is the mobility, and the mobility is K, which is permeability divided by viscosity. So whenever the permeability increase, the velocity increase whenever you have the same pressure gradient. Whenever you have heavy oil, the velocity decrease. If you have light oil, the velocity increase on the same pressure difference. Okay, this is also very quite simple equation. Okay, then the third equation which we have is the compressibility equation, and the compressibility equation showing what's the impact of a change of the pressure on the rock, what's the impact of a pressure on the fluid. The density change with pressure is function in the compressibility, and the rock itself also, whenever you change the pressure, the rock expand or shrink. And this expansion or shrinking, we call it compressibility factor. Okay, those are the three equations which we are using together to bring another equation. We call it diffusivity equation. I don't expect any student in the oil and the gas field has not seen this before he gets graduated. This is the equation of the diffusivity equation, and I think I can tell you this is the most popular equation in oil and gas. Okay, and it can show a second derivative of pressure with time with distance plus what are this is the radius, this is the radius from the well. Then the first derivative is function in the pressure change with time. Okay, and this is function, we have a parameter there we call transmissibility parameter, which is phi, the porosity multiplied by viscosity multiplied by the total compressibility divided by permeability. This is the most important equation which you have it in the reservoir engineering. I can't even tell you, you don't have even more sophisticated equation more than that in oil and gas. If you know this and quite familiar with it, you are quite familiar with the reservoir engineering. this equation is quite important because it gives a relationship between pressure with distance. If you have a huge reservoir, you have a pressure everywhere, and you need to know the pressure everywhere, okay? And the change in the pressure with time. You can inject or produce, but the pressure will change. And after the change of the pressure, you need to know the pressure over distance and the pressure it change with time. This is really important equation. I'm stressing that many times. And this equation is used in well testing. So this is the base for well testing. If you are well test analysis, rate transit analysis, pressure transit analysis. If you need to calculate the permeability from well test, you need to calculate the skin and every parameter you're getting from well test. This equation can be under certain assumption can be solved analytically using what we call line source, Laplace equation, whatever you have, and you get out of it. You can get war transit analysis or pressure transit analysis. Okay, rate transit analysis or pressure transit analysis. But for the simulation, we are not solving this equation analytically. We solve this equation numerically, and I will show you how can we do this in a couple of minutes. Quickly again, بالعربي المعادله ديت مهمه جدا لانها بتوريني العلاقه بتاعت البريشر مع التايم والديستانس. يعني انا اقدر بريدكت البريشر بتاعي في اي مكان وفي اي توقيت، في اي مكان وفي اي توقيت. دي اهم حاجه في الايكويشن دي، من خلال العلاقه اللي بين البريشر والتايم والديستانس اللي موجود عندي في العلاقه دي. اوكي. Why pressure is important? Pressure is important because if you drill a well, you need to produce. It will produce 100 barrels, or it can produce 1,000 barrels, and can produce 15,000 barrels. Depends on two parameters. Depends on the pressure, because the pressure is the energy, and depends on the property of the rock. Okay, so that's what this equation gives you this relationship. Okay. And it will help me to understand the saturation everywhere. Saturation, which means which type of fluid exists anywhere. Okay, and this equation, which I have shown you, can be solved in one dimension, like I show you here. So this is grids. You can bring the pressure in this grids and this grids and this grids as one layer, or it can be in two dimension, like I'm showing you here. It can show you we can solve get the pressure on two dimension, x dimension and y dimension, or in a three dimension. Okay, you can have the pressure everywhere in the vertical direction, on the x direction and y direction. Okay, this is quite simple. What's numerical simulation? Now it's time to solve this equation. This equation is really a challenging equation because it's non-linear equation on second derivative. It's really challenging. It's not that easy to solve this equation. So the only way to solve this equation is to use mathematics. Okay, and I expect all of you have studied the mathematics, and I can show you in a second how the equation from the first derivative. If you have equation like this, a change in function f over x distance, you can just calculate it by this is the equation by subtracting the value of f function f at location I minus f fi -1, which is the point before, divided by distance. To make it simple, it's the slope. The finite difference or the derivative is the slope. And to calculate the slope, you just need 2 points and divide them by the distance. Okay. تاني بالعربي. ديت انا عاوز اجيب افك الديريفاتيف ايكويشن عندي. الديريفاتيف ايكويشن اللي عندي ديت في اتجاه الاكس. انا عندي فانكشن اف تتغير متغير في اتجاه الاكس. عشان احله باخد نقطه على الكيرف واطرح منه النقطه اللي قبلها واقسمه على المسافه. ده بيديني الميل بتاع الخط اللي هو في الاخر خالص اللي بسميه الديريفاتيف. Then I have different ways so that I can calculate the derivative here or the slope here from forward or backward. That's what we call the first one. If you are using the point where you are and to calculate with the previous point, which is the back point, this is what we call it backward finite difference. If you use the forward point like that, we call it the forward finite difference. And if you have the second derivative, you subtract the forward and backward together to calculate the central finite difference. Those are three ways to solve the derivative by mathematically by finite difference. I know this is really difficult, but I have to show you quickly before I go to the core of the simulation. Then this is the first derivative. If you have the second derivative, it will be a relationship between forward and backward finite difference. Okay, this is how it looks like at the end. The only thing I'd like to know about it, if you remember Frere series and etc., you will find here what we call it a truncation error or the remaining error. This is really important simulation. I'd like to remind. I know even people working on the industry using simulation day after day, they are not fully aware with this, because I know most of the engineers don't like simulation or equations, mathematics and equation. But this is really quite important factor. This factor, what we call it, if I solve the equation, the derivative, I still have a remaining error at the end. Whenever you have bigger distance, like delta x is much bigger to calculate the slope, this number will be much bigger. If you are using smaller steps, which is x, you will have a much smaller truncation error. Again, whenever you are going in higher orders, you are getting less truncation error. This is the different ways to solve the equation: the forward difference, backward difference, central difference, and usually the central is much accurate than both forward and backward. And the accuracy depends on choosing formulation and the size of a step, either in time or space. I will stop here to give some practical flavors about simulation from here for those already familiar with the simulation. Any one of us has built a simulation model. Our geologists usually give us what we call it fine grid size. Then we are, as reservoir engineers, try to upscale this. I will show this in more details a little bit after a while, but I just try to build the link. Our reservoir, the reservoir engineer, because of the capabilities of the machine to run the fine grid system with time, it will take so long time to build this to run fine grid system, which is million of cells. Over time, it will take so long time by existing machine. Then the reservoir engineer to start to build what we call it upscaling, which means reduce the number of cells in the simulation. By reducing the number of cells, we are maximizing the step size. Some people run the models on a monthly basis, some people run on annual basis. By increasing the time or increasing the size of the grid, you are increasing the truncation error. And this is another error coming to your calculation from nothing, just only because of upscaling or increasing the time step. Okay, so this is really important. That's why some people, before they start running the models, they upscale their models, and the upscaling we do it on different trials for upscaling to ensure that we have the minimum truncation error. This is the truncation error again, arise due to residual. I'm almost there, and I'm finished with the diffusivity equation. So if you have any question, please ask me.
I've received 2 questions.
Okay.
First one, which is the least important factor in diffusivity equation that if excluded not impact the overall equation?
Now again, first, what the most important factor?
Which is the least important factor in diffusivity equation that if excluded will not impact the overall equation?
Yes, but I don't. While driving the equation, we have some assumption at the beginning. Like for example, you have, which is not showing here. This is the solution of the equation, by the way. If I'm getting back to here, you will find another factor, which is the change of the pressure with distance to the power to the square power. This equation assumes that we have low compressibility fluid. Okay, if you have compressible fluid, you will have little bit changes to this equation. But this equation represents everything, representing the mass balance, so it doesn't have a lot of assumption. Except in this this area now, assume homogeneous reservoir, at least for the grid, homogeneous grid, it assume the fluid into the grid is still low compressibility. Other than that, we don't have so many assumptions. Okay, but this equation, like I said, it gives you depends on the change of the permeability, porosity, and viscosity, compressibility. It gives you the change in pressure the change of the pressure in 2 dimensions, radius and time. Okay, which is distance and time. Okay, I don't know if I understood the equation correctly or not, but it has some assumption as well. Low compressibility, which we are showing here, it's one of the assumptions that the change of the pressure over distance is quite minor on the radius, delta radius. So it's also we have eliminated some factor from this equation. Okay. What's the other question? And if who asks the question is not satisfied, he can ask the question again. What's the other question?
Okay, which is the most common error when one develops this equation?
Common error while developing this equation?
Yes.
Like I said, when this equation is quite exact solution. The problem when you solve this equation using finite difference, then you have to accept some error. Like I showed right now, the truncation error is one of the issues. Okay. Other than that, if you fulfill the assumption, you're in a good situation. But this is equation still exact solution. Okay.
What is the equation used to calculate initial oil in place in dynamic model?
Say it again, sorry. What's it?
What is the equation used to calculate initial oil in place in dynamic model?
So again, you don't have so many equations for calculating the volumes. Even in dynamic, what's the difference between dynamic and static for calculating the volume? That you calculate. Okay, let's remind ourselves by the volume equation. Because you calculate volume from material balance, mass in, mass out, change the volume. If you have the change the volume, mass in and mass out, you can calculate the volume inside already. Like if you have the balloon and you have a change in the fluid, you have some fluids getting out, some fluid going in, for example, or anything. You can use the pressure. You can use the pressure and the fluid properties to calculate the volume from material balance. But the volume itself, from the static point of view, It's the pore volume, which is the porosity multiplied by the area multiplied by the thickness. Usually, when you are calculating this, you need to use the beta O to convert from the reservoir to the surface, and this is beta O, for example, is it's changing with pressure, and the pressure is different from place to another place. So if you are considering, if you ask me about the static volume, which is the initial oil in place, I can tell you the only impact of dynamic volume is how to calculate the fluid properties over distance. Because over distance, the pressure is not the same. Another factor which is coming to you, use dynamic, is how to populate the saturation. Because you need the saturation as well to calculate the hydrocarbon pore volume. If you know to know the hydrocarbon pore volume, you need to know the saturation, and to know the saturation, you need also to build the dynamic model. But again, the volume itself, if you are asking about the oil in place, just only the level of accuracy coming from the dynamic is how you calculate a proper beta O over distance, how you calculate saturation over distance. Okay. Other than that is the material balance, and I am quite sure everyone is familiar with material balance and how you are going to calculate the volume for material balance. Okay. I need to move because this is really difficult area for everyone, and it has so many equations behind that. I'm just trying to simplify it. You understood now that we have a diffusivity equation, that we drove this diffusivity equation from three main equations: Darcy equation, mass balance. Okay. Then we knew how to solve the derivative into the equation using finite difference, and we understood about the truncation error. Now, if you need to solve this equation to calculate all the parameters, you need to understand that you need the pressure, which when I discussed the mass balance, I said the pressure it changes with time. Then, if we solve for the pressure in the next time step, okay, because actually you have parameters, the fluid properties. The fluid properties in the equation, like beta O, you have viscosity, you have density, and you have two. When you calculate solving the equation, you have initial pressure, and you're going for another pressure. The pressure going from B1 to B2, for example. Then, if you calculate, for example, the viscosity, formation volume factor, and density, at which pressure you are going to calculate this fluid parameters, you need either calculate it at B1, which is the initial condition, or at B2, which is the next condition. If you calculate the parameter as the next condition, you are calculating implicit, what we call it implicit solution. It's really challenging, I know, but I expect you studied this, and if you didn't study, you need to study before you get graduated. If I'm teaching this for engineers, I'm not going to take engineers through this comprehensive equation, because for me, I do believe that a student should know about this equation. If he doesn't know about this before he gets graduated, he will not ever know about them after graduation, because usually engineers love using machines and softwares without getting to the core equation. Anyway, if you calculate the density, viscosity, any other fluid properties at the next time step pressure, we call it implicit. Okay, that's why you can see here the density calculated at n+1, which is the pressure which we try to calculate. يعني assume دلوقتي ان انا عندي 2 تايم، عندي التايم اللي انا واقف فيه دلوقتي النهارده، التاريخ بتاع النهارده مثلا 16/10/2000، وانا عاوز ارن الموديل عشان احسب البريشر بعد شهر. بعد شهر ده after 1 month from now, it's what we call it the next time step. The next time step we call it n+1. Then if you would like to calculate the density at n+1, we call it implicit solution. Okay. and etc. I will not take you through. And if you calculate the pressure at the next time step after 1 month, we call it, and the factor property depends on the pressure at the next time step. We call it implicit pressure and explicit. Explicit means that you are calculating on the time of now and the factor of now. يعني, for example, the pressure today is 1,000. The pressure after 1 month, we don't know about it. If you use the 1,000 to calculate the fluid properties, we call it explicit. We know it. We understand what it is. لو احنا نستعمل البريشر بتاع النهارده اللي احنا قايسينه وعارفينه اللي هو 1000 PSI, we call it explicit solution. For example, if you whenever you build a simulation model, you must know from the beginning the saturation. If you use the saturation of now, of today, we call it explicit saturation. But you would like to predict the pressure, we call it implicit pressure. Okay? To make it usually this is even more. If you use explicit saturation, explicit pressure, the solution will not be accurate because you are using the time, the pressure of today and saturation of today to calculate all the parameters, which is changing over time. That's why the explicit solution is not accurate, is the lowest accuracy, but you can calculate it quickly and easily and in very small time step, small time. Okay, if most of the people calculate what we call IMPES, implicit pressure and explicit saturation. It's much more accurate than the explicit, and we usually use it for composition simulation. I know this is really difficult. I will take you through practical. If you can manage to follow up with me, it's really lovely. Again, I advise each engineer, you cannot graduate without understanding everything I'm telling you. You must study this over a year. It's not in one session, but I cannot jump without showing you what you have to have learned. Okay. Then the implicit, this is the most accurate solution that you solve all the equation for the next time step. This is what we call it fully implicit. Okay, and this will take so long time, and usually we use it for compositional analysis and equation of state. Okay, for now I'm not going to discuss any more about the equations, and I will accept some questions. Any questions, Karim?
Okay. Yes. In comparison to Boltzmann model, how diffusivity equation will deal shale and tight formations, where permeability is almost zero?
أنا مش سامعك على فكرة، ممكن تقول تاني. I can't hear you. ريبيت يا كريم لو سمحت.
Zahran,
I think Karim has some.
Can you hear me?
سامعك.
The question is, in comparison to Boltzmann model, how the diffusivity equation will deal shale and tight formations, where permeability is almost zero. Would you like?
Okay. يعني if the permeability is zero, you don't do calculation. Usually, you don't do calculation in shale. يعني if you have shale layer, you don't do calculation inside the shale layers. Okay. Because permeability is zero, then the equation doesn't have anything to calculate. You don't have change in saturation because how will saturation will change if the permeability is zero, and if the saturation doesn't change as well, the pressure will not change. Okay, so this is something I will show it later in the practical. So we don't calculate this equation into shade. Just this equation to solve the change. This is the next slide now. احنا ليه عملنا المعادله دي؟ Why we have this equation؟ يعني to make it simple. ليه؟ Because I need to know the pressure of oil, water, and gas everywhere. يعني انت عندك reservoir, you have a reservoir. This reservoir, for example, like Aramco, they have very long reservoir. It's something like a few hundred kilometers multiplied by 100 kilometers. الغوار, for example. This reservoir is kilometers. So you need to know the pressure everywhere. يعني أي نقطة anywhere into this reservoir, you need to know two things: pressure and saturation. خلاص. Pressure for oil, water, and gas. And usually the pressure should be the same for three of them in case you are neglecting the capillary pressure. So if we don't have capillary pressure, you have one pressure represent. You need to know. لو أنا هحفر بير هنا, if I am going to drill a well anywhere, what will be the pressure I will find in my well? So the diffusivity equation help you to calculate the pressure everywhere over the hundreds of kilometers. But when you drill a well, you don't drill a well to produce water. You drill a well to produce oil or gas. So you need to know the saturation of oil and gas everywhere. ماشي. But the diffusivity equation مهمتها الوحيدة, the only what we need from the diffusivity equation to calculate the pressure everywhere and the saturation everywhere. Simple. In my reservoir, why I need the pressure? Because the pressure defines the rate. يعني انت if you drill a well into a reservoir with high pressure, you produce higher rate. If you drill a well and in a depleted reservoir with low pressure, you produce lower rate. Okay. How do you know that you need water flooding? If the pressure is depleted. So you need to understand how much will be the depletion. If you inject this amount of fluid, how much will be the pressure? If you inject in a buoyant water, how it looks like in the saturation everywhere. It's understood? This is what we need from the diffusivity equation. The diffusivity equation, we need pressure and saturation. Simple. Okay? This is showing what's the difference. When I say water pressure, gas pressure, oil pressure, this is only due to capillary pressure. You should be familiar with capillary pressure. I will have another session for rope properties. That's why I'm not going to discuss much more about capillary pressure. Then also you have saturation. You need to calculate the saturation of oil, water, and gas. And each rope should the total of saturation of oil, water, and gas should be 100%. Simple. Okay. This slide only to show you what's the difference between analytical tool and numerical tool. Okay. If I'm calculating the pressure or saturation using the finite difference or numerical solution, it will be continuous like this. Buckley leverage give you a piston-like, which means if you are calculating the saturation, you will find one saturation at a certain distance. If you are using simulation, you will find a change in saturation between grids. Okay, that's why we call it dispersion. What means dispersion? If you are going to model two wells, one injector, one producer, if you use Buckley leverage analytical solution, the water front will move with time. So if you say after 1 month from now, where will be? For example, assume that we have injector here, producer here. The distance 100 meters. If you inject inject water from this well today, next day the water will be here. The day after it will be here. Then after 1 month it will be here. After 2 months it will reach the well. But if you are using simulation, the water will be dispersed everywhere and it will reach your well in a couple of days. That's what we call it dispersion. Here, what's more accurate usually is the exact solution. Buckley leverage is the exact solution, and this is more accurate than the simulation here. Okay, this is really also quite important. I know this is. If I have the time to teach you everything, I will link this to what we are going to learn after a while. Okay. But if I'm moving forward, okay, this is what we call dispersion, and to overcome this you have to have very small grid size. For those are not familiar what I mean with grid deviation, I will show what does it mean grid and why we need grid, okay, or cells. This is the difference between. That's why some people ask me this question, and even I have been asked this question in interviews. When I went for a couple of interviews before I joined Shell, and I usually ask what's the difference between simulation and analytical tool? Do I use analytical tool or I use simulation? When I use material balance, if I'm using simulation, do I need to use material balance or not? If I'm using simulation, do I need to use Buckley Leverett or not? Okay, this type of question you'll be asked on very high advanced interview. Okay, and you must know the difference between the volume. I had a question since a while. The oil in place, for example, you can calculate the oil in place using simulation, numerical solution. You can calculate the oil in place using static, the STOIB from the geologist from the static solution, static parameters. You can also calculate the oil in place from material balance. You must know the difference between the three. For example, the geologist, when he calculates, he doesn't predict the change of saturation or the change of beta O, which is the fluid properties with pressure over distance. He used one parameter for everywhere, or for example, the interpolated parameters. Okay, but in the simulation, you calculate each fluid properties depends on the pressure. Because the pressure, and at least as simple as that, the pressure is increasing with depth. لو أنا عندي reservoir, thick reservoir, the pressure in the bottom is higher than the pressure on the top. That's why the viscosity in the bottom should be, if both of cases above the bubble point, for example, the viscosity will be higher in the bottom than the top. The formation volume factor in the bottom will be lower than the top of the shallow part from the reservoir. That's why the accuracy of the simulation in calculating oil in place little bit higher than the static volume. The material balance using a different technique. You must know those differences. Here, for example, you must know Buckley Leverett. It gives you a front, sharp front, saturation over distance, over time. Simulation doesn't do this. Simulation give you saturation over all the grids. So you can find the grids has water saturation. Even the water can, in reality, reach your producer. Okay. Then, if we are going to solve this equation now, I'll take you. Sorry, I will skip those slides and I'll get back to them to tell you what I mean by grids. Now we have the diffusivity equation. انت عندك diffusivity equation اللي هي combination between Darcy material balance, I'm repeating, mass balance and compressibility. So we decided that we will solve this equation using finite difference. What means finite difference? Which means I need, for a certain point to calculate the pressure at this point, I need the next point pressure and the previous point pressure. So how to I solve this? We are building a grid to give you the finite difference, so that you can calculate the pressure by subtracting the pressure in the next grid and the previous grid. احنا لو شايفين ده للطلبه بقى, I'm sorry for the foreigners, but I need to explain this. I will explain two languages as well. انا دلوقتي حليت الفاينايت ديفرنس. طب انا عشان احل الفاينايت ديفرنس عاوز 3 نقط. لو انا بحل في الاكس دايركشن، ولو انا بحل في الاكس والواي عاوز نقطه في قبل في الاكس ونقطه بعد في الاكس ونقطه قبل في الواي ونقطه بعد في الواي، which mean انا محتاج اقسم الريزرفوار بتاعي into small grids. يعني انا بجيب الريزرفوار بتاعي، الريزرفوار اللي هو في الحقيقه ريزرفوار، واقسمه لمكعبات صغيره، وابدا الوكيت البريشر والساتوريشن والبيد فيها. كل جريد بتمثل ريزرفوار صغير، تيوب صغير. I will repeat it in English. If I'm going to calculate the diffusivity equation for my reservoir, which is 3 dimension, I have to split my reservoir into very small, tiny grids, so that I can calculate for each grid the pressure and saturation, permeability, porosity, and net porosity. Okay, so that's what I'm calling the grids. So the big reservoir will be divided into small grids. Those grids will cover the x dimension, the y dimension, and z dimension. في حد مش فاهم لحد دلوقتي؟ Does anyone don't understand me? Because I'm going into the practical now, showing you how to build simulation. If you don't understand anything until now, you can ask me. This is the end of equations.
Guys, let me remind you that you have 2 options in order to ask questions.
Karim?
The first one is to write your question down through chat box, and the second one is to use raise hand gesture, and we will allow you to open your mic. So kindly, if you have any question, please follow those instructions. I think we have one question.
Yes, very nice.
The question is, could you please explain the difference between numerical and physical dispersion?
This dispersion, the problem that you will not understand before I show you on the grid. You have this grid, for example. This has water, okay, and whenever this is what we call to solve the finite difference equation, okay. You need to have grids, yeah, which means that, like I show you here, if I get back to this plot, this one, sorry, to solve the finite difference at any point, you need to have a point before and point after, okay. That's why we call it finite difference. We are not any one of you, whenever they get the derivative of x 2x with x, they calculate it 2x, the derivative of 2x is 2, for example. If you are getting the derivative with x direction, if you have x squared 2 x squared, and you are getting the derivative with x direction, it will be, for example, like 2x. This is what we call exact solution for the derivative. Now we are not using the exact solution, we are using a finite difference solution, which means to calculate the derivative at each point, I need another point forward, another point backward. Well, to do this with a reservoir in 3 dimension, you need to have here a small box, okay, a small box here and a small box. This is the x direction. That's why you can see here, to build a simulation model, you need to have something like this in x direction. We call this grid, another grid, another grid. You have 3 grids. For 2 dimension, you need grids in this direction and the grids in this direction. This is what we call the grids. For 3 dimension, you have those grids. Then, if I'm getting back to the last slide, which I show you after a while, if you build it for a big reservoir, it will be the cube full with grids everywhere. But what mean dispersion? If I'm going to calculate, let's assume that Today is the time step 0. Today 16 which day is today? 17 of October 2020. This is today, time step 0. And you need to calculate the pressure after 1 month. Calculate the pressure and saturation. If you inject water in any one of those grids, the water will move as far the water saturation higher than the critical water saturation. So assume here with me that you have here 50% water saturation, and you calculate the saturation in the nearby grid. The saturation here will move from this grid to the next grid. Then, because the next the saturation in the next grid is higher than the critical water saturation, the saturation will keep moving. This is not like to make it simple. If you have a cup of water and spill cup of water, the water will go everywhere. But if you have cup of water and spill it on the floor, water will go everywhere, continuous phase. But in reality, in the porous road, water cannot move everywhere because there is permeability, and the water will move like a piston-like. In the simulation, it will show you like exactly like when you spill water on the floor. On the Buckley lever, it will be show you like piston-like. The water will move behind the oil as if it's piston. Okay, this is the main difference. This is what we call, this is not physical. This is analytical solution, and this is finite difference solution. Okay. I'm sorry, I teach this class in many hours, but I know this is challenging for you. Unless you studied this before, it will be difficult. And it's a little bit of shame that I spent some time with all universities, and most of them are not studying the simulation last year. That's why I insisted that I teach this. I know that we have people on the call that are experienced, they expect me to show cases and show achievement, but this is really important. Okay, another question.
Engineer Muhammad, I'm sorry to interrupt, but I received one question in chat. What is the difference between circular and triangular points on this grid?
I don't know what you are to. Oh yes, in this grid, this injector producer. Sorry, this is the circle is producer, and we show what's if we have injector or producer. Okay. This injector and producer. I'm showing you from aerial dimension and from full field. After a while, I will show you how to build a model in reality, and my colleague Mahmoud will help you to show you this on the software. So be patient with us. We'll show you everything on the software. Okay, I will show you a couple of examples from real example. Then Mahmoud will show you how to do this calculation on the software. So this is, if you build this grids, you need to add the wells. These wells can be injector, can be producer, can be gas injector, gas producer. I'm just, before I move, I will tell you a couple of refreshment. When I joined GAPCO 2005, after a while, I joined the simulation team. And the simulation team usually at this time we were only have a small team called field study team. And my first job came to me outside the local companies was because of I managed to build my first model. When I showed it to my boss, he was surprised at this time because the company was not now GAPCO has a lot of people are capable of running simulation. But in the past, while I was my colleagues, I think we have a series of people. Usually, those people, anyone work on simulation, quite familiar with simulation as a theory and tools, usually got a job outside. I have a couple of colleagues now working for E&I. I think Wael, many people. I will bring you some other people with international experience for another session, next session. But I'm just telling you, the simulation was like the most lovely tool that you can help you to solve anything at that time. That's why everyone worked for the field study and simulation gap before me went to either to Gulf, Arab Gulf, or working for international companies right now. That's why simulation is really challenging, but it gives you a value. Definitely, to have this value, you have to have integrated view. Okay, but simulation is one of the fantastic tools that can help you to do whatever you want to do. You can solve the will test here using numerical simulation. You don't need to go use the analytical solution, because analytical solution has its own assumption. But if you need to have RTA or BTA, you can solve it in the numerical solution. You build this grids, like whenever you build these grids and add the problem to it, exactly you are like a civil engineer and an architecture engineer. The civil engineer builds the external of the house, and the architecture engineer builds the interior of the house. And you can do anything you want afterward. يعني تاني زمايلي الخريجين لو انت كيبل انك تران سيميشن كويس، تعرف تعمل الجريد ده 3 دي جريد اللي انا وريته لك ده، وتحط فيه البروبرتي بتاعت البروستي والبرميبيليتي والنت جروس، وتحط البريشر والساتوريشن، انت من هنا تعرف تعمل اي حاجه في الريزرفوار بتاعك. You can understand how many wells you can drill. You can know what's the distance between wells. You can predict the well test analysis data. You can predict anything you want. You will be on the top of your machine, like playing with magic. On one condition, you can integrate numerical simulation with other tools, integrate with other disciplines. Okay, that's why numerical is one of the fancy tool which we have it in, and not everyone is quite familiar with it. Okay, I'm getting back to the application. If no one ask any other question about theory.
There is one more question.
So after we solve the okay, go ahead.
How the number, cells, or size of grid can affect the occurrence of the simulation?
Number affect what?
The simulation.
Affect what?
The occurrence of the simulation.
And anyway, number of grids. Usually, if you need to have the most accurate simulation, you have to build very tiny, small grids. And for example, let's assume together a field with 10 kilometers distant length, and the width, for example, 1 kilometer. Okay, and the thickness 100 meters. What will be the size of assume with me, if you have a grid 1 by 1 by 1, 1 meter multiplied by 1 meter multiplied by 1 meter, a very small grid. This is a small grid. How many grid I want to simulate this reservoir? Can anyone help me? I have 10 kilometers multiplied by 1 kilometer multiplied by 100 meter. How many grids with dimension of 1 meter multiplied by 1 meter multiplied by 1 meter? I need to simulate my reservoir. I think I can allow the mic, anyone to calculate this, do this calculation. $10,000 multiplied, this is the 10 kilometers, 10,000 multiplied by 1,000, which is 10 million until now, multiplied by 100 will be a billion. صح? I need a billion cell to simulate a reservoir with dimension of XYZ for cells 1 multiplied by 1 multiplied. You can imagine this 1 meter. 1 meter is not that small. This billion cell will take from you ages with any machine on the ground, on the earth right now, to run this model. And what I'm showing you now is I'm telling you about 10 kilometer by 1 kilometer by 100 meter. This is really a small field, really small field, very small field. If you for small field, if you have 1 meter multiplied by 1 meter grid multiplied by 1 meter square grid, this means cubic meter grid. This means that you need a billion of grids, and billion of grids will take from you ages. That's why we need to upscale, build bigger models, bigger cells. Usually, people in the practice, let's assume instead of having a billion, will build a grids of 100 meter multiplied by 100 meter multiplied by 100 meter. How many grids I want? To make it easier, simple. 100 by 100 multiplied 1 meter, which means you will have 10,000 volume. The volume will be 10 of each cube will be 10,000. And if you divide 1 billion by 10,000, you will get 100,000 grids. Okay. Then to simulate your reservoir, you need 100,000 grids. This will be manageable. That's why you need to first of all think about the machine software that help you to solve this this mathematics. That if you run it on cubic meter, it will be fantastic. You will get the best result. The truncation error will be quite low. For example, the dispersion issue will not be there, and all the error which you have it will be eliminated. However, you cannot do this because there is no machine, no real machine, laptop, I mean by or workstation can solve this it will take from your workstation machine and the software. Okay. And why software is important? Because algorithm, how the algorithms work inside, because each has 6 equations to solve. For each grid, 6 parameters. For each grid, you need to know saturation of oil, saturation of water, saturation of gas, the pressure of water, pressure of gas, pressure of oil. 6 variables. For this 6 variables, you need 6 equations. If you have a billion of cells, you need 6 billion of equations. Can you imagine that you solve 6 billion equations at each time step? Last week I was working on a model that has 47,000 time step. Can you imagine with me? You have 6 billion equations calculated at 47,000 times. This is a huge amount of equations, a huge amount of calculating time. That's why calculating, defining the cell dimension and orientation is comprehensive task. Need a lot of work to be done correctly. Okay. Most of the people in the industry usually use, for example, like I said, 200 meter multiplied by 200 meter on the thickness. It can be 5 meters, something like that. But it can be different from case to case. If you are going to model well-test analysis, you need much smaller grid size. If you are modeling a big field, you have to have a bigger grid size. Okay, this is what we call a grid size. Moving forward, I just need to tell you how you build a model. Okay, to build a model, first of all, you need to understand the geology, because before you need to understand geology to convert it into grids. Yeah, those grids will represent your reservoir, and I'm bringing you some nice pictures from all over the world for reservoirs. Usually the geology is, for me, I love the geology. although I'm not really well experienced with geology, whenever any geologist start teaching, I get attracted so quickly. I get fascinated with the geology. And this is the lovely thing about working as oil and gas industry. Yeah, geology is one of the flavor of it. Okay, and to understand the geology, you need to understand the existing phenomenon. Okay, usually when we were taught the geology, it was taught to us as if you have a mountain and this is the reservoir, how it was created. You have a mountain, you have whatever photoelastic reservoir, the wind come or the water coming, and it start to bring the sand out of this mountain or whatever it is and move it over distance. And most of the reservoir is built by water, for example. That's why it has the same dimension like water canals, like seas, like lakes, and everything. But the only difference that our reservoir is full with sand or carbonate instead of being full with water. أنا عاوز تتخيلوا معايا إن الليكس البحيرات الترع الحاجات دي كلها هي ريزرفوار، بس الريزرفوار ده بدل ما هو مليان ميه هو مليان ساند. ماشي؟ this reservoir is full, this lake of sand full with oil and water and gas, and it's buried under 3 kilometers, and you need to predict where is this lake. So this is an example for a lake, for example. This can be a reservoir. If you drill, if you are following up with me, if you drill in this water, you will find a reservoir. If you drill outside, you find shale. You don't find anything. Outside, this is a shale. So your first job as a geologist or reservoir engineer to know where is the reservoir. For example, in this picture, this is a reservoir. If you drill here or drill here or drill here, you will not find you are not going to find the reservoir sand, or you will not find hydrocarbon. Okay, that's why you need to understand how it looks like the outcrops and how it looks like your reservoir. If you understand, this is one of the reservoir. This is Mississippi Delta. Your reservoir can be something like this. Can be like this tree, and you have to predict all those channels. Then if you predict this pathway, then you need to make grids for it. يعني انت لو عرفت المسار ده, first job, you must know this is what's tricky. You cannot see this under the ground. After this was built on the ground millions of years ago, different layers of sand, shale, carbonate coming on the top of it, making 3 kilometers, a few kilometers on the top of it. That's why you need to predict how it looks like this under the ground without seeing it. This is the beauty of it. Tamam? That's why this is a really difficult as well, because if you drill well here, you will not find the reservoir. If you drill well here, you will find the reservoir, but it will not. If you use it as injector, it will not support a well producer in this location. It's really challenging. Going back to Egypt, because I think as far we are from Egypt, we have to predict. If any one of you try to predict the Nile Delta and assume that the Nile will be our reservoir, and we buried this Nile and fill it with sand, it will be really difficult. It will going everywhere. You have branches on the delta. You have this branch of the Nile coming. So if you need to penetrate the Nile here, it will be good. If you need to drill well here, you need to know where is the branch of delta. Okay, this is the reservoir. This is the first step you need to know about it. How to predict the reservoir. Where is it? If you predict the reservoir, you grade this reservoir. Make it as small cubes. Simulate it as small cubes. Okay, that's why the cube will not. I show you the cube will be something like if you have this grids, you have grids beside each other. Here, if you go to the picture, it will be finding the small grids here, through small grids here. Then you have grids here, grids here, grids here, and grids here. All those will be grids. Okay. This is a thickness. This is a reservoir, exactly a reservoir. This outcrop. I told you about outcrops in the last session. I'm bringing you. This will be a reservoir. If you drill a well here, you will find the reservoir. If you this will be your reservoir. If you drill a well here, you will find the reservoir, and you will find a small fault here. That's why this fault, if you drill here, you will it will come to a reservoir a double of time, for example. This is another picture for us, and imagine this is a log. If you drill a well, you will find. If you drill the well here, you will find the reservoir, and if you drill a well here, you find the reservoir, and you will find. But if you inject here, they are not connected. Different bars. Okay. Then, if after you understand. And to build the grids like this, you
كريم.
ايوه يا نجم، سامعني بوضوح؟
اوكي.
كريم.
Yes.
Did you miss a lot because I think I was disconnected? Kareem. Can you hear me?
Yes, sir. We can
I can hear you.
Engineer Muhammad, please go ahead, continue, please.
Now we managed to build the grids. We understand the geology. We understood the geology. We built the grids. Now we can build the simulation model. Okay, and to build the simulation, this is a different type of grids. Then we need to bring to the grids the different properties. For example, this saturation map, for example, or permeability. You will find the high permeability in the middle, like a channel, and on the edges you don't have permeability, for example. You need to know to have the porosity and distribute the porosity for each grid. You need to drill wells and see where is the wells. You drill your wells here, there, and everywhere. That's why you need to define your wells. That's why first step that you build the grids, and the grids to mimic the reservoir, like I showed you in since a while. And this grids, then you need to bring the property, like what type of property I need to have in my grid for each grid. For each grid, you need to have porosity, for example. You need to have permeability. You need to have fluid property. You need to have net to gross. Net to gross, what does mean? Do I have reservoir here or not? Do I have shale or sand? Do I have shale or carbonate? So this is the reservoir presence. Then you need to have where is your wells are drilled from this reservoir. Okay. The porosity, for example, first of all, you don't have permeability everywhere. You just drill a couple of wells. You know the porosity. You can predict the porosity based on the drilled wells. Or some people bring it from seismic by seismic inversion. If you have seismic and you have seismic attributes, you can bring porosity everywhere. Then, by using core analysis, this small core, you have for each core porosity and permeability. You can, from this porosity and permeability, you can have a relationship between porosity and permeability, and for each grid, if you know the porosity, you can calculate the permeability. Then you have something showing you the situation where is, for example, where is the water. This is a depth map, but anyway, it can be, for example, if you have the contact here, you have, this is the water, this is the gas, the oil, this is the gas, for example. This is not a saturation map, but will be something like that. If you drill well in the gas, you will produce gas. If you drill well in the oil, you will produce oil. If you drill well in the water, you produce water. The next step is, after you build this this 3 dimension of the grids, the Diffusivity equation will help you to calculate the pressure like this for each well. This is the pressure for each well. You can hear block J, block K, block M, for example, different blocks. You will have the pressure, simulated pressure. This is calculated using what? The Diffusivity equation. And this is actual data calculated from the well. And your job as a simulation engineer to ensure that this actual data match what the model giving to you. If they are coming aligned to each other, meaning that you build a fantastic model. That's what we call it history match. The first step is to ensure that the model bring to you what we call it actual data. This is a pressure. This is, for example, a saturation map. And to match the saturation, you need to match the water cut, the GOR. If you have BLT, you can match it. If you have 4D seismic, which 4D seismic you can calculate the saturation over time, then you can match the water like this. So the model, whenever you drill a well anywhere, it will bring you a simulation. This continuous line, the simulation. Your job as a simulation engineer is to match the actual data. How we match actual data? By changing the parameter of the grid. For example, you change the porosity, you change the permeability, you introduce barrier, fault, for example, you introduce a different rate, change to rate of permeability. That's why you can match this, the water cut as well. This is another example for the water. The red one is a case. Something you need to know, you will never know the truth of the reservoir. You will never know the truth. That's why you have different scenarios for the reservoir. You can say this channel, if I get back to this channel, for example, you can say your channel can be, for example, this way. It can be this way, can be this way. So you can build different scenarios, because definitely you will not know this is Mississippi, you know it because you have seen the Mississippi on the from the aircraft. You have you can have picture from the sky from the universe to the Mississippi. That's why you know you see the Mississippi. But how you know this if it's a reservoir? By drilling wells, by seismic. That's why you will not for sure know where is the reservoir everywhere. That your job is by drilling well, you have built scenarios. You will have multiple scenarios. You might have fault here, you might have something tectonic forces here, and etc. You might know that if you drill here, well here, and drill well here, you will connect both of them here and forget about this part, although they are not in direct communication. If you drill injector here, a producer here, this injector will not support this producer efficiently. It will take ages until it supports the producer. Remember this: if this is a reservoir and you drill injector here and producer here, although you find the same sand which is here, you find it here as well, but it will take ages until it communicate. So if you need to support the producer here, you need to drill injector here, not here. Although this can be very long injector, however, the support will be much better than if you drill a producer here. Okay. Going back, this is what we call it history matching, which is bringing the reality, actual data on the simulation. Okay, Then you build scenarios until you match the actual data. This is different scenarios. This is different prediction for the same scenario. Okay, with different rate of permeability. If you change the rate of permeability, the situation changes. This is a case with using different permeability. This is another case for different permeability, and this is the actual data. This is the actual data, and whenever you change the rate of permeability, you get closer to the actual data. This is your job. Last thing, which I'm going to present in 5 minutes, a real case. This is a real field. And that's it. You are saying something? Okay. This is a real case. I'm just ending with a real case, then I hand over to Mahmoud. This is a reservoir. This is another reservoir, like what you try to work. This is a surface map. And we decided this was the production. This is oil rate. It started with 3,500 barrels. Then with time, the rate declined because definitely because of the pressure and the water cut increased. Okay. We decided to drill here 5 spots. Then and we tried the 9 spot as well. The pilot was 5 spot. Okay. Then we switched the 5 spot to 9 spot, and we'll show the impact of drilling it as well. This is the reservoir. If I get back here, 5 spot was here. Then we converted the 5 spot to 9 spot. The oil production increased once again from this a real case. The oil production increased from a couple of hundred after implementing the pilot 5 spot. The production increased to 3,000 after we implement the full field water flooding for the whole field. The oil rate increased to 12,000. This is how it looks like in the beginning. This is how it. This is a this is a nice spot. Okay, and how it looks like. We can start converting wells, and you can come back to the map. You will find here we started drilling a lot of injectors, and this was the 5 spot. But later on, we converted all those wells here for injectors. That's why we had 5 spot, 9 spot, and the 9 spot you can see here. You can see the wells get converted, and you need to get it predicted. How we can do this? You cannot do this by analytical tool. You need simulation. So to predict this from this reservoir, before you implement the full conversion of the wells, you need just only to have this prediction. You predict the water, you predict the gas, you predict the oil, and you predict the different pattern until you get something like that. This is give you the highest recovery factor. Whenever you have the highest recovery factor, you start drilling wells. So this simulation save you $millions of drilling wells and getting failure. You drill wells, and by drilling the wells, you are safe enough because you already did this on the simulation, on the machine, on the laptop, on the computer, on the workstation before you go and execute it in the reality. Okay, I can take a couple of questions and then hand over to Mahmoud to show you real cases on the simulation. This field in the North Sea, for example, by the way. Kareem, do you have any question, or I can hand over to Mahmoud?
No, you can hand it if you want to do it.
Mahmoud, I think Mahmoud can, and I will take any other question at the end.
Hello?
Sorry, Mahmoud, for keeping you that long time.
No problem, Mr. Zahran. Okay, I think now we can move to the application or simulation software. And actually, I like to deliver this part of the session in Arabic because the main audience for this session is students in Egypt. So I think I will change to Arabic. ازيكم عاملين ايه؟ I don't know. I didn't hear you.
Yes, we can hear you.
Can you hear me?
Yeah.
Okay, good.
Okay.
Okay. As I said, I will deliver this in Arabic. I know that most of the audience are Egyptian students. Am I right?
Yes, but we have foreigners also.
Okay. So do you think it's better to deliver this session in English?
It's better to deliver it in a mix between English and Arabic, if you can.
Okay, no problem with that.
Okay, thank you.
Okay.
Thank you.
Before Mahmoud take over, I just need to announce something for the next session. I will have a friend from Shell Holland. He one of the expertise in the simulation. He will join me for 10 minutes next. He one of the best reservoir engineer in Shell. He will join me in the next session. But I'd like you to join this session. I invite everyone to join this session. He has 2 PhD, and one of them was recognized as PhD in UK. And he expert matter in integrated reservoir modeling. I'm not going to tell any more about him because I'd like him to be on the call while I'm introducing him. On the session after, which is the field development planning, I will invite another friend who used to work for another international company, British Petroleum, and he will show you a lot of examples from all over the world. But I'd like to, again to stress that if you continue with us, our schools, field development school, you will meet expertise from all over the world. Okay, thanks.
Okay, first of all, let's give you an overview of the simulation software called T-Navigator. There are a lot of simulation software in the market, but I'm a technical support for T-Navigator, so let's talk a little about it. Actually, the simulation software is split into different modules. According to the process of simulation. We don't, as a reservoir engineer, do all the process, or geologist or geophysicist do all the process. We have integration between the different teams. The first who works on the model, who are the geologists and geophysicists. They take the seismic data, logs, and they use this data to populate the reservoir with the static properties like porosity, to know if there are some faults, to know the geometry of the reservoir, and if we can have different distribution of properties also, maybe, and most of the time the properties are not uniform in the reservoir. Then after they finish the first step, and I don't want you to think that this step is finished and we move to the next one. Actually, it's an iterative process. They just make a handoff to reservoir engineer. Reservoir engineer use the data to populate the model with the dynamic data, with the BBT analysis they receive from the laboratory, and use the relative permeability data, and put in the model the production data that we were recorded at the field. And then they try to do the simulation and do the history matching process. After doing the history matching process, most of the time, all the time, there's a gap between what we predict and what we have in the field. So we go back to the first phase again, the geology, tell us, okay, we have uncertainty in some areas and we can do some changes and do some uncertainty analysis. And we can change the mountain in a certain range, because out of this range, the properties we won't be reasonable to have. After that, the reservoir engineer can take the model again, do some calculation on it, go back to the geology, edit some properties related to BVT, related to permeabilities, and do the process over again until we have a good match, and we say, okay, this reservoir model now is reliable, and we can do it to do a prediction. As I told you, the first step that we do is populating reservoir, do the reservoir structure, populate it with some properties, so we'll use the module of geology design. And actually, this module is used by geologists and geophysicists, so won't talk about it. The next module that we use as a reservoir engineer is called model design. After we have the static model, we populate it with PPT. But also we won't talk about that. I won't talk about a real case model that we have. And actually, I will talk about the features of this model and some feature relating to water flooding project. We can now import the model. Please, if anyone have any has any question, please interrupt me and I can answer to you and then go back to the presentation again. Okay, first of all, let's talk about the initial properties of the model. We have initial properties like depth, porosity, permeability. They are designed by the geologists. And we can see the distribution of these properties in our model. You can, using T-Navigator, you can use a cut, you can look at different layers. When we go to the 2D, we can use layers and can see the property, the distribution is posted in every layer. Also, we can see the distribution of this property using a histogram. This is for all the initial properties or the properties designed by a geologist. For the calculated properties, as Mr. Zahran has shown, that pressure is already implemented in the model by reservoir engineers, and we can say that pressure and saturation are related to each other and related to the capillary pressure. So this is those properties are defined by the reservoir engineer, and when we initialize the model, they are distributed according to the data we have inserted to the model. We can use some graphs to do some analysis on the wells data. We can analyze production data with time. We can see that the oil rate, also the production of water versus time. The main properties that I want to show you today regarding water flooding project are using the tracers to track the flow of water from injection wells to production wells. We can go to the grid properties. We can go to the 2D. If we want to input a tracer in the model, we can go and do some filtering to search for the wells that we want to use for putting a tracer. We'll assume that it's called well 1. Okay, and we need to go to a time step that we will use to schedule the tracer to be in the well. So actually, sorry for that, but we'll go to the property, we will go to the control, and we will define a tracer for this well. And then we will do, press save. As a step, time step 32, we have used a tracer for well 1. So after running the simulation, pressing the red button, we will run the simulation till the end of the schedule we have defined for the simulation. But I have run this simulation to save your time, so we will look at cases that we have. I used well 1 and well 34 to input tracers. And we have a profile that shows the distribution of tracer in the reservoir. Let me show it to you.
Mahmoud, can I stop you for one? Can you adjust? This is really lovely pictures. That's why I'd like to stop you for a second. The 3D with wells.
Okay.
Mahmoud, can you get back to the 3D with wells?
I'm hearing you.
Because I need this one. Yes.
Yeah, I want.
That's what I was telling you, that you need to build your reservoir and you can have all your wells. So those are the wells which you can see on Mahmoud 3. You just imported all the data. That's why you have all the wells, and you now can get the data of any well by using simulation. So this is what I want you to understand. This is almost like 52 wells drilled in a multi-layer reservoir. Okay, you can continue, Mahmoud. I'm sorry for disturbing you.
No problem. Okay, so as Mr. Zahran said, that this is the model, the grid of the model are distributed to small grids, and we can know the size of this grid using the block statistics. Here we will know that the block size along direction X is 80 meters, and along direction Y is also 80 meters, and along direction Z is 0.3 meters. As we can see that the grid is very large compared to the grid that Mr. Zahran, it can be like 1 by 1 by 1 meters grid. So actually we have to divide the reservoir that we had into a reasonable size, because dividing it into very small grid sizes will make it very hard to computationally to calculate the reservoir production data that we want to predict. So actually, and you don't do it one time, you do it a lot of time. As I said before, it's an iterative process. You can do it like for 50 times before get a good match. So actually, it can't be that tiny small grids, so you can make it more reliable to do your calculations and do the future prediction. Going back to the water flood, as I showed before, we can input the tracer into the well, and we can have a profile that shows the tracer's flow in the reservoir. Actually, from the time steps, we can show how the tracer propagate in the reservoir. Using the play button, we can see how it propagates.
Mahmoud, معلش, you give me 1 second. Just can you explain what's tracer? I can quickly. I can tell you the tracer. Whenever we need to understand the connectivity between injector and producer, we add some chemicals to the water, and then we trace these chemicals. So, for example, you can have polymer or whatever surfactant that you can inject it with water on this well one, for example, and over time you need to see where is this water is going on. But you just only trace this water. This is what we call it tracer, and we use it for surveillance for many reasons, to understand the permeability between injector and producer, to understand how the level of connectivity between injector and producer, and where is the water is going. This is quite important. That's why I'm just explaining what means a tracer. What Mahmoud is doing, I think now simply many reservoir engineers cannot do it in the oil and gas industry. How to match the move of the water particles within the reservoir carrying the tracer. Okay.
Exactly.
Keep on, Mahmoud.
Okay, now we have seen the tracer. There's another beautiful property in T-Navigator that we can know the streamlines. If we have a water flooding project, there is a property that we can see the streamlines. Going back to the 3D view, looking at the top of the reservoir, we can use streamlines, but we cannot see the streamlines because the grids now are populated with the pressure property. So we will hide the grid properties. Okay, now we can see the flow lines or the stream lines from injection wells to production wells. We can edit the visualization of these lines using this button. We can edit the line width, and we can edit the density. The density here represents the number of cubic meters per every streamline. So actually, if you increase the density to say 15, the number of lines will decrease. I think it's taking some time to load. Yes. The number of streamlines decreased when we increased the density. You can see here we can see that this is a reducer, and this one is a reducer, and this one is injection well. So we see that well 25 is effective by well 11 and well 19. Also in the 2D view, we can see the streamlines by layer. Here we can activate the streamline. Also we can deactivate the grid. And we can see it by layer. If we change the layer number, we can see the streamlines in every layer. Also, we can go to the graph and see how the tracer against time. So for well number 1, as we use the tracers there, okay. We only will use the production data for well 1. Sorry, injection rate. So we can see that for well 1, the injection rate is changing with time. And if we have a well that is near to well 1, we can see here the production data. But let me first, yes, this is this well. With the advance of time, we can see the production rate that was received from tracer 1, or I mean well 1. As a general process of populating the dynamic model with data, we use production data from our reservoir and populate these tables with data, and also determine some schedule as we specify at which time there was a step to perforate a well, or to maybe close a well, or maybe turn a well from production into injection, and the other operation. Maybe we'll do some hydraulic frac, so we will increase, we'll edit the properties again around this well. Actually, this was an overview of the simulation module. I want to go back to the overview of the simulation process. And I want to tell you that there's a process, there's a module called assessment history matching. This module will help you to reduce the gap between the real data received from production data and the data simulated by reservoir. So actually, this module in some way helps you to make experimental design. If you have uncertainty with a specific property, you can use a range of values, and it can show you how the production changes, or the properties that you want to fix, how this changes with different input variables that you have insert into the model. Actually, this was a short overview of the software, the navigator, and I want like if anyone have any questions, please let me know. Okay, don't you have any questions?
We don't have any questions, Engineer Mahmoud.
Okay, that's
Please
it.
keep moving on.
Okay.
So I think we spent much time this time for explaining the simulation. I just again I would like to thank you again, thank Mahmoud for this presentation. I think you can see that everything we explained in theory can be executed easily in the simulator, and this is we have seen how can we import the geology, import the properties, then how can we generate forecast for everything we want, including well production, performance, and etc., including even the matching of the tracer. And this is one of the really important surveillance that we are doing in the fields to predict the communication, because as I explained since a while, geology is really complex. That's why we need different tool to understand the connectivity between different producer and different injector. What's streamlined simulation showing the relationship between each injector and producer. It was quite helpful tool. And what I'd like to announce in this meeting that we are going to introduce this software to the future soon. So this is one of the faculties we decided to deploy the software, and we might teach the people how to use it. This will add a lot of value to the people. So keep learning going on. Be patient with us. I know that we are teaching a lot of theories because we understand we are talking to students. In the last session of the school, which we are delivering to you, we'll show you examples, cases from all over the world. But the value will transfer to you if you understand very well the theory, because pushing the button is not the most challenging part. The most challenging is to understand the theory and how to integrate it with different tools. This is how it makes you a unique engineer with the real challenges in the market right now. Thanks a lot again for the time. Thanks a lot for the organizers. It's really fantastic event. Thanks Dr. Ismail and Dr. Muhammad Gharib for supervising and supporting those type of sessions. And I'm looking forward to meet you again on the next session.